Hey, year 12. Hello. Okay, so today's lesson is going to finish off the AS level specification for Edexcel, which is really great. I'm just trying to pause the video on my other laptop. There we go. Also just checking all my screen settings and whatnot. Yeah, okay. Check my camera settings and my audio settings. Yay. All right, guys. So, okay, we're going to be looking at alkenes today. So last lesson that I had with you guys. So this is primarily aimed at Julian, Dixon, and Winkett. But of course, like to think that any of the other AS students I've got want to watch it. It's just going to cover all the reactions that alkenes go through. I'll go through the specification at the same time and also go through the mechanism of electrophilic addition and also a little bit of polymerization as well. Just having myself a cup of miso. Right, I'm going to get straight into it. I'm not going to faff around, so let's do share screen. There we go. I'm going to go for that one. Get rid of that. Hide. Cool. Okay, so reactions of alkenes. The first thing, of course, I went to your specification. So addition of hydrogen using a nickel catalyst to form alkanes. I'm pretty sure most of you guys don't need any help with that. That's just reduction using a nickel catalyst to turn an alkene into an alkane. There are little details in here, though, I do want to mention. That process of reduction, so I'm just going to add that to my notes over here. So we know that we can, so reaction one, let's go reactions. And number one is reduction. Reaction one is reduction. So we're going from an alkene, so ethene. By the way, you wouldn't ever do it with ethene. That would actually be, that would be a completely pointless exercise. You are changing a molecule which is used in making polymers. Remember, it's not plastics. That word is banned in A-level chemistry. So that's the process, and it's done. Nickel catalyst, nickel cat, and it's a solid, by the way, and it's done at 60 degrees Celsius. You need to know all that. So this is the reduction of enes to anes. Now, that process is called a non-selective reduction. What that means is it is indiscriminate. It will reduce any. Suddenly realized my other one's actually playing. I need to pause it. There we go. Non-selective reduction. It'll reduce everything. That's actually probably the most powerful reduction tool that I have in my arsenal. I can't do it in school, although it seems totally reasonable for me to do that. I wonder if it's actually possible. I don't have a stream of hydrogen. We don't have hydrogen gas in our inventory. I have to make hydrogen gas, which is a pain. But that there would be this particular reaction that I've given you, this one here, that would be absolutely pointless. The reason being is that that has a higher value than the product does. Higher value than the actual product. Because this is going to get used as fuel. We know that ethane's used as a fuel. You know, it's a hydrocarbon. It's going to burn. Yeah. Whereas the alkene is going to be used for making polymers. And that has a much greater value. So you'd be turning something of a higher value into a lower value. You'd never do that. That would be that is a frivolous bit of chemistry right there. So the question is, where is this used? Well, it's used in vegetable oils. Because veg oil, I'm just going to say, I'm mentioning this as part of it, because veg oil are said to be unsaturated fats. Unsaturated fats. Now, just to show you what one of these, you've got this is called a glycerol backbone. I should actually draw it for you properly, really. I can actually draw you a vegetable oil molecule. So it's got a 3-carbon backbone. 3-carbon backbone, and this actually is called a glycerol backbone. Yeah, the reason being is the molecule. I'll draw the rest of it. So, by the way, you'll realize I'm now showing it. This is an ester linkage from GCSE. And then they have big, long carbon chains, about 16 carbons long. I'm going to put on however many I can fit on my screen. There we go, until I run out of space. I'll put one more. And then every now and again, so by the way, what you're looking at right there, that's animal fat. Yeah, that's animal fat right there, saturated fats. And then you go lob in a double bond or two to make it polyunsaturated. There we go. That there is vegetable oil. I'll put on all the bonds as necessary. These are just hydrogens, by the way. These are just hydrogen atoms. I'm not going to bother with using all the... I'm not going to bother drawing all the H's. I'll be there for a week. I've made a mistake. There we go. So this is vegetable oil. And you guys eat this all the time. It's a liquid at room temperature. Just to point out that each of the double bonds adds an actual kink to the chain. I'm tempted just to show you another image of that particular molecule. So if I do vegetable oil... Oh, I don't want to do that. I just want a vegetable oil molecule. Vegetable molecule. I can't spell vegetable. It's amazing. Vegetable molecule. Images. Oh, there you go. You can see all the random double bonds. Yeah. But the double bonds add a kink in the chain, as you can see there. So vegetable oil is an unsaturated molecule. Now, vegetable, of course, is a liquid. It's a liquid. If I call this veg brackets L, yeah. If I now add hydrogen to this in the presence of a nickel catalyst at 60 degrees Celsius, I will add hydrogen to every single double bond. Every one will lose. I will add a hydrogen across there. Double bond breaks. Double bond breaks. Add one here. Double bond breaks, add one here. Double bond breaks, add one here. Double bond breaks, add one, add one. Double bond breaks, add one, add one. Yeah, it is completely indiscriminate. It will just add them to everything. Yeah, now what I have just made there is margarine. So that process hydrogenates, this is called hydrogenation, and I will turn it into margarine. Margarine. There we go. And it just causes it to solidify. It means it becomes a solid because as you add the hydrogens, the chains straighten out and they lock together better. So the increase in surface area increases your London dispersion forces, causing an increase in boiling point. So that's hydrogenation. You need to know nothing else about it. Right, reaction number two. Reaction number two is halogenation. Halogenation. Now, you'll never actually write down that word in an exam. You really won't. Yeah, but all this is taking an alkene, and I'll actually draw the H's on this time. There you go. There's my alkene, and I'm going to add a halogen. So fluorine, perhaps. Chlorine, perhaps, bromine, perhaps, or maybe even iodine. I can add any one of these. The one that you'll always see in exams is usually Br or Cl2. The reason being is fluorine's incredibly reactive. It's explosive on reaction with anything. It'll actually shred an alkene. People might say, how do you actually add a fluorine to an alkane or an alkene in that case? And I'm like, they use free radical substitution, but even that's hazardous. But we can certainly, most common ones you're going to see at the exams are going to be these guys. You tend not to use iodine because it's a solid, which means the reaction is going to be slow. You could potentially heat this and the iodine will sublime to become a gas, but not ideal. So if you add this, you produce a rather lovely product because the double bond breaks. The double bond breaks open. It was here, yeah, and it's broken open. And now I've got two positions that I can bind things to. And I'm going to add them across the double bond. Now, you guys saw this at GCSE. This was not complicated. But the problem now is you now need to give the mechanism for this. Now, the mechanism for this process, and it's the same for all alkenes. So you can do I'm going to make my pen a little bit thicker. So alkene in, and that's actually kind of important. If you get alkene out, it's elimination, but alkene in mechanism is called electrophilic addition. Said it, wrote something else. Electrophilic addition. It's called that's the mechanism. I'm not doing very well today. There you go, electrophilic addition. So let's see what that now looks like. Okay, so we have an alkene go in. Now, alkenes, you guys all got told GCSE, they're reactive, and they are. This is because the double bond is reactive. It can break relatively easily. But also, the reason why they're reactive is because this area here, I shouldn't draw an arrow now, should I? This area, I'm just going to highlight it. This area here is electron rich. I'm going to go, this area is electron dense. That's what makes them reactive. Yeah? What that means is when they come into contact with a halogen, let's go for bromine water. Yeah? So we know that bromine is diatomic, travels on in pairs, and when it's a gas or liquid, it's brown, but when in water, it's orange. Now, these two shouldn't really react. They shouldn't really do anything at all. The reason being is that bromine, I'm just going to remove that. Bromine is non-polar. That there is non-polar. What that means is this should not really react with this shouldn't react. Therefore, should not react. But it does. And it actually reacts very, very, very satisfactorily. I wouldn't say vigorously. You don't see, it's not like a huge exothermic reaction. It's not violent. It's just, it happens relatively briskly. It takes only a few seconds and you'll see it disappear. But it should not react, but it does. And so, question that's often asked on exams, why do halogens react with alkenes? Now, your answer to that answer is the fact that on collision, because the double bond, on collision, the Br2 molecule is polarized. So what that's saying is it's saying that because of that is polarized due to electron dense double bond. There we go. So what's happening here? This is where my other tablet's gone to sleep. I'm just going to quickly reset. I seem to have nobody here. Not that I really care. So here's what's happening, folks. When it's approaching, when it's colliding with it, the electrons are distributed evenly, so it's non-polar. But during the collision, one of the bromines is going to hit it first. You can't have both hit simultaneously. So the electron-rich area here causes the electrons in this bond to move this way. And so what's going to happen is you're going to get induced polarity. You're going to get this. It's now going to become polar. Yeah, because the electron-rich area repels the electrons in the bond. You don't have any to show those electrons in a mechanism, but that is the first bit in a mechanism. Find the delta. Yeah, now I need to point out how important this arrow is. Yeah, because this arrow is commonly done badly. Yeah, common answers. There you go. You're going to lose it. The arrow is not touching the double bond. Not okay. Yeah, ambiguity. You've got to start where the electrons are. You're literally going to touch that bond right in the middle, and that means you're going to break it. Remember, if you're going to break a bond, you start in the middle of it. And it's going to tell us that we're going to make a bond to the bromine. Now, at this point, we now realize that bromine already has a bond, and it only makes one. So this bond here, literally, this is actually quite an unusual curly arrow, because it tells us we're breaking this bond, but making a new one to that bromine. Now, the problem is that bromine already has a bond. We've got to break it. Now, curly arrows move away from each other. Once again, I need to break a bond. I'm going to start in the middle. So I start in the middle, and I go away from the other curly arrow. Electrons repel each other. So now that that's broken, what we now need to do is that bromine now needs to join onto this molecule. So we get an unusual intermediate. The double bond has broken, just as we said. Double bond is broken. And I've got to choose someone to put the bromine onto. I'm going to put it onto this guy. And now, of course, I also have Br minus. Now notice a full charge appears, so I'm circling it. All full charges should be circled. It's good practice. Right, now the other thing is, though, that this carbon here, this carbon, before the reaction, had this carbon here. This one had a 50% share in these 2 electrons. It owned one of them, 50% share in 2. Well, now that curly arrow just says, well, that bond is broken, and those electrons have now gone here. This carbon had a 50% share and now has a 0% share in 2. It's like losing an electron. It becomes fully charged. This is called a carbocation. And in fact, it's a primary carbocation. Now, I'll come back to that later. It's a primary carbocation. So now, it's last step in a mechanism. This is a 2-stepper. That's going to join on. And that's it. Your mechanism is over. The double bond broke in step number 1, and the bromine bond broke. And then the bromide becomes a nucleophile and attaches onto the carbocation, which kind of makes sense. The positive and negative will attract each other. So at the start, this molecule here, the bromine, which is non-polar and shouldn't react, is actually acting as what's called an electrophile, which is an electrophile as an electron pair acceptor. It's coming from that bond. So that there is the addition of bromine to ethene. Let's have another go at this. Let's do something different. Let's do ethene. Let's do ethene plus HBr. So we're going to react this now with HBr. Now, lots of students often draw that out like that, and it's a really bad way to go. It's not going to be good for the actual mechanism itself. So what we need to do is we need to realize that step number 1 in any mechanism is find your polarity, find your deltas. And this is polar. This is much more reactive than the previous one. That's not a great place to have this for a mechanism. These have to collide. You can't put them miles away. Now, it goes that way. Yeah. Now, the reason why is because this is a region of electron density. So it's the electrons are negative, which means it's going to attract a positive. The molecule is going to face this way. Now, once again, now with all EA mechanisms, the double bond reaches out. We're going to break the bond, which means we start in the middle. Yeah, to break a bond, you got to start in the middle. I need to produce a nice short curly arrow to that hydrogen. Next, this bond here needs to break. Yeah, so we need to break that bond. Start in the middle and go to the Br. And that's now over. So step number 1 has been finished. Now the question is, who do I want to put that onto? I can put it onto either one in this case. The double bond is gone. Double bond is broken. Let's straighten it up. Yeah, those are the H's. That were the originals. I should have color-coded everything. And I'm going to add this H to this guy. Why not? Just because I did the other one the last time. Yeah, and of course I've also formed bromide ion, which is fully negative now. Circle the charge, and it now picks up a lone pair because it's now going to act. Its role here is a nucleophile. Now, people often say, why don't we call this nucleophilic something then? Why don't we call this nucleophilic addition instead of electrophilic addition? The reason being is because this here is the original attacker. This is your electrophile, an electron pair acceptor in stage 1. And that then is going to hop on. And we're done. So it's a nice straightforward mechanism. We've just had a look at the hydrogen halides and the halides themselves. Sorry, and the halogens themselves. And what you see is that one of them produces a dibromo, dichloro, a di substitute, whereas this one produces a mono. Sorry, not substitute, addition, a di addition. Because at the end of it, with the halogens, you end up with a 1,2-dibromo if I draw the product. Yeah, this becomes 1,2-dibromoethane, no longer an ene, but you get 2. On this one, however, you don't get that. You just get a bromo, And you don't need a number, but it's good to put it in. 1-bromoethane as the output there. So let's have a go with this with a slightly more complicated molecule, because these will always get more and more difficult. So the next one is I'm going to react ethene. You'll notice I'm sticking very carefully with ethene. This will become clear in a moment. I'm going to react this with concentrated sulfuric acid. Concentrated sulfuric acid. And you have to know this, folks. Yeah, sulfuric acid. Here's what it looks like. This is what H2SO4 actually looks like. If you've had me as a teacher all year, then you'll probably have already seen it. I try and draw it as often as I can. It's a horrible thing. It's a bit gangly. So the first step in any mechanism is find your deltas. And the delta on this case is the H and the O. And I only need to label one of them. I could label the other one if you want me to, but it makes no difference because it's not taking part. I need to break this bond. Yeah, break the double. So in order for me to break a bond, you start, that says now I'm breaking it. And that's going to be attracted and form a bond with the H. Right, but the problem is the H already has a bond. This is the bond it already has. Well, I need to break it. I'm going to start here, and curly arrows move away from each other. So this is going to move to the oxygen. So at that point, look what I now have. Step number 1 produces this. Once again, straightening them up. And this is the hydrogen I've just attached. That now becomes fully positive. But what does the sulfuric acid become? The sulfuric acid now looks like this. There we go. If you make a positive, you must make a full negative. Right, now this is going to be awkward for me now because those dots are a bit close. And in order to make a bond with a lone pair, you must leave from the middle like that. It's really important that you learn these little subtle details in order to make it easier for you to understand. There you go. Doesn't even matter that I've gone all the way to the C. I could have stopped when I got to the positive. They wouldn't have minded. So, and at the end of it, I'm going to form a ethyl hydrogen sulfate. What a gross molecule that is. So, I'm going to keep with some continuity here. There you go. Just to explain to you where the name comes from. Yeah. So this is ethyl. I should do it in yellow. Try and keep some continuity between it. Ethyl, because it's a branch off it. Hydrogen. Ethyl, hydrogen, and then sulfate there. Ethyl, hydrogen, sulfate. There you go. So it's exactly the same mechanism. It's just a little bit more tricky because you just have to remember the structure of sulfuric acid and you can't make it up either. People often say, can I make it up? And I go, no, because there are alternative structures that aren't correct. But you'll realize that the mechanism is the same. This is electrophilic addition of alkenes. So, okay, next reaction that we need to look at is, you realize, I said earlier that I'd remember to say the see us later for the primary carbocation, because what we've now been doing, we've been doing electrophilic addition. This is EA, electrophilic addition. Electrophilic addition of, what about the unsymmetricals? Unsymmetrical alkenes. So what about something like propene? Now this is much more tricky. The reason being is this is an unsymmetrical molecule. The double bond is off to one side. Now what this means is if I was going to now react this with HBr, let's just choose hydrogen bromide, keep it easy. Step 1, find your delta. Right, first thing is the double bond's going to break and it's going to join, because it's electron rich, electrons are negative, it's going to join to that H, and that break there, that bond is going to break. Right, now a question now arises. Which carbon do I put it on? There's 2 pathways. I could go this way. Double bond is gone. Here's the originals. These are the originals. Let's now color code this. Yeah, let's just do this H here as red. So where's that going to go? It could have gone to here. There you go. The alternative structure it could have formed is this. Again, double bonds gone. Put on my originals. There you go. Here are all my originals. And I could have put it onto the other carbon. There. Now, what you'll notice is that the carbocations are now different. This one here is a secondary carbocation. Secondary carbocation. And this one's a primary. Now, the whole point of primary, secondary, and tertiary is the idea of what's called the pi effect, the positive inductive effect. So the question is, why do we need to categorize these? Because in reality, they're slightly different. Here's the actual picture. Right, and what you notice is the secondary carbocation has a slightly smaller charge. Now, the reason for this is what's called the positive inductive effect. Positive inductive effect. Pi effect. Is it affect or effect? Pi effect. Effect. It's effect. Pi effect. So the positive inductive effect. And what this says is that the carbons next door are going to push a small amount of their electron density towards it and reduce the charge on that. The electrons in these bonds, just to explain to you what this means, because I am very aware that there might be people who watch this that haven't had all of the rest of my other lessons. So if we were to zoom in on this, we'd like to think that this bond here, these bonds are between carbon-carbon atoms. These should be non-polar. The electrons should be dead in the middle. However, this carbon here is fully positive. What that means is the carbons next door allow a very small amount of drift. So what they do is these electrons just drift ever so slightly. I'm just going to draw their new positions in green. Those electrons drift ever so slightly towards the positive carbon. I'm actually going to show you this in real time, how it actually changes. So when it got formed, this is how big the positive was. And then the pi effect kicks in, and the electrons drift this way. Yeah, they move ever so slightly, and they give a little bit of more of their charge. I put that there and there, and this is reduced in size. And then these do the same thing as well. These move a little bit as well and reduce it further. So a secondary carbocation, the charge is much reduced compared to a primary. So the positive inductive effect produces a more stable carbocation. Produces a more stable secondary carbocation. Whereas the primary is less stable. Less stable. Only one positive inductive effect from one carbon. Doesn't have much of an effect. So what that now means is we're now going to get a really odd distribution. We get 95% of this guy, and that is now called the major product. And we're going to get 5% of this guy, commonly now called the minor product. So you will get a bit, but just not much. I shouldn't really call them products because at the moment these are intermediates. But I don't really mind doing that in a minute. So second step in the reaction, let's go for the major pathway. In fact, let's go for the minor pathway since it happens to be there. The bromide ion now has its pair of electrons, now hops on, and it's done. So I will actually get two products. If I take an unsymmetrical alkene like propene and I add to it HBr, I will get a major and a minor product. I will get a major with the bromo on the second carbon because of the second carbocation, secondary, and I'm going to get the minor product with the bromine being on the first. Yeah, this is the minor and this is the major. And they pick on this heavily. I ought to show you some exam questions, but I don't want to spend too long doing this. I'm just quickly going back to there. I just want to quickly check. So we've done reactions with nickel and catalyst. We've done the dyes substituted haloalkanes, halogens to produce, yeah. And then hydrogen halides, we've done that one. The addition of steam in the presence of an acid catalyst to produce alcohols. That's actually the sulfuric acid one. I'll come to that momentarily. Electrophilic addition of bromine and to ethene done, and electrophilic addition HBr to propene. We've done that one as well. Using carbocations and knowledge of relative stability of carbocation intermediates is expected. The curly arrows start of either bond, lone pair of electrons. We're okay with all that. Describe. Okay, cool. So there's only one more bit to do, which is the alcohol bit. Okay, alcohols. So alkene to alcohol. Now, I now need to tell you that there's actually, annoyingly, two processes here, and one of them is standout. So what I'm actually going to do is, I'm just going to say the first thing that we're going to have to do is we're going to take ethene, and we're going to do the most common route and mechanism for it, which is we're going to do ethene plus steam to make ethanol. This is the one they always tend to ask about, but they can ask you any one because you can apply this mechanism to all of them. Okay, and this is done with a concentrated H3PO4 catalyst. It's also an equilibrium, and it's also done at 300 degrees Celsius at 60 atmospheres. You've got to know that one as well. You should have been told that, though, in equilibrium for Unit 2. Okay, so what does this now look like? So we need to be able to do this stepwise. So full mechanism for this. Ethene. And I'm going to react it with phosphoric acid. Now, can I just point out, sometimes they like to swap this for sulfuric because it's slightly easier to draw, but it doesn't really make a huge amount of difference. There's just another OH group. There's my delta. Right, break the bond, reach out, break the bond, go to the O. Product from this. I'm going to form ethyl hydrogen phosphate at the end of it. So there's my ethane, and now I've got O fully negative. I'm going to go POH, OH, double bond O, right? And that's going to hop on. So I've now formed this structure. This is what I've now formed, ethyl hydrogen phosphate. Just going to flip it over to make it easier to understand. There we go. Right, now this is now extremely polar. And now it can be attacked by steam. Yeah, water molecules are weak nucleophiles, remember? I'm just going to show those there. I'm just going to put them on. Right, so let's now zoom in over here. Lone pair on the oxygen, and it's going to attack the C, and that's going to break away. Product. I've now got this structure. Fully charged on the O. And our phosphoric acid is back again. Oh, switched to sulfuric, bad habit. If people are wondering whether or not you have to be able to do this, the answer is yes, to a certain extent you do. People are going to be saying, what do you mean by a certain extent? They can ask you to do any one of the steps in this, any one of them. And the phosphoric acid is being regenerated. This is the regeneration of the catalyst. The phosphoric acid is taking back its H that it gave away originally, and the OH group is being put on. So that there is how it's actually happening during that process. I'm going to tick that one off. Right, last one, which is a bit of a weird one. You don't need to know any mechanism for this, which is great. This is just a nota bene. NB, an important notice. Important notice, if you take an alkene, ethene, I should just do alkene. Nota bene, if you have an alkene and you react it with acidified potassium permanganate. Yeah, dark purple guy. Yeah, you react with this, what you will produce is a diol. Go figure. You'll just add two, the double bond will break and you'll add two OH groups on either side. And that's a standout one that you just have to know. You don't need to worry about anything else. You might have to balance an equation, but not overly challenging. Right, so that actually, I'm almost at the end now. So there's the oxidation. Here's this one here. Oxidation of the double bond by acidified potassium permanganate 7 to produce a diol. Tick on that one. Right, alkenes, monomers, and polymers. Okay, so a quick one on polymers. I think I'll go down on my reactions. There we go. So can I just point out, this is still a very, very brisk look at this topic. I still need to do some exam questions. I'll do that at a later date. But the last bit is polymers. So you guys know that these are, of course, very particular for alkenes. So the alkene polymers are otherwise known as addition polymers. Yeah, that's the type of polymers they are. And this comes straight from GCSE. We recognize that we can take an alkene. You'll notice I draw it slightly differently in a polymer setting. I tend to straighten up the H's rather than doing them out at an angle in like what I call a spider diagram. I tend to flatten them out because what I'm about to do is I'm going to take an n number of these. I'm going to break the double bond and I'm going to stretch it out and I'm going to turn it into the polymers. Now, there are certain polymers you just have to know. That's polyethene, of course, because this was ethene went in. And I've now joined many together to form polyethene. Not complicated. Yeah, but there are certain plastics you have to know. So you have to know, number one, you have to know PVC, polyvinyl chloride, otherwise known as polychloroethene, proper name now. There we go, I'm drawing it out for you there. This was made from chloroethene. Not overly complicated, saw it at GCSE. You also need to know PTFE, again, GCSE. This is polytetrafluoroethene, and this is one which has 4 fluorines on it. Otherwise known as non-stick, made from tetrafluoroethene. There you go. There are other ones as well. You have to know acrylic, and I'm gonna make a mistake here. You also have to know acrylic. Acrylic. And acrylic is a rather bit of a nightmare substance because it's actually alkene acetate. It's an alkene that's got an ester on the end of it. Acrylic. I can't remember what the actual monomer is, which is oh, there you go. Polymethyl methacetate. Yuck. That's rather acrylate. It's an old name. So, by the way, quickly, okay, do you know what? Exercise. Let's translate this into the monomer. So what I want to do is I want to snip that. I'm just going to snip it. This is exactly the kind of question you'll get at A-level. Yeah, they'll give you this and then say, draw the monomer. Totally reasonable. That's what I've just had to do. I've looked up the polymer. It's given me that picture. So what's the monomer? Well, those are the carbons that have the double bond in it. So I had a CC double bond between those. Let's get rid of those. The long gones are gone. These are gone and gone. Right, this carbon here has just got 2 H's attached. So let's just put 2 H's on it. Yeah, there's the 2 H's. This one has got a methyl group, a CH3, and it's got an ester group attached as well. There you go, CH3. So there's your acrylic. And again, they do ask it, so something to keep an eye out for. Just quickly, going back to the document at the top, disposal, pretty sure that was on there. I wonder how many which ones are also with names. Be able to describe addition polymerization of alkenes and draw repeat units given the monomer and vice versa. Discussed. Understand how chemists limit the problems of polymer disposal by developing biodegradable polymers. Okay, so polyalkenes are all non-biodegradable. Yeah, the reason being is they're non-polar and the carbon-carbon bonds are very strong. So they can't be attacked by water, or they're inert. They can't be attacked by water and they can't be attacked by bacteria. So they invented polyesters and polyamides, condensation polymers, which are technically deemed as biodegradable. To remove toxic gases from incineration, yeah, the other thing we do is we burn them. We burn them to give us energy. The problem is that causes toxic gases, which are not great. It says removing toxic gases. So that will be capture and storage of carbon dioxide. That'll be using alkali scrubbers, filters to be able to remove any acidic products. If you burn anything with Cl in it, you'll make hydrochloric acid as a byproduct. You're also going to get dioxins. You're also going to make sure that you burn an excess oxygen to get complete combustion. So you're going to make CO2 and water. But not overly complicated. I'm going to look at this. I'm going to do a second webinar. I'm actually going to end it there today. And that brings us to the end of Unit 1. Right. Let's bring us back. Just removed it. Let's go back to that one. There you go. Right, guys. I hope you found it useful. Please make sure you have a look at some questions in the booklets on the sheet that I've put on the that I created, and then send me any questions that you've got. I'll see you soon.